we succeed? Should have done. Why haven't you done? Hurry up. Okay, move over for Colin. Damn it. Come on. Let's go to vision. All right. Browse. Okay, is there anybody who is, if you're not here and you're supposed to be, raise your hands, because we're waiting for you. And we didn't mean to put up RTF. We really still are Internet Research Task Force. And with any luck, I have now updated the slides. So welcome. I'm not going to give you slides. I know you've memorized the note well, so we're not going to show it to you, but there will be a test at the end of the session. And just so you know, IRTF abides by the IETF's note well. So if you've seen it multiple times, you've seen it for us as well. We just changed it so it says IRTF. This is the week of a change of command in the IRTF, and I want to introduce you to Colin Perkins, if you don't already know him, and welcome him. He'll be running things from here on. And we have 3 presentations of ANRP speakers, the Applied Networking Research Prize. There are normally 2, but one of our presenters was unable to attend last time. And they're going to be terrific talks about large-scale hard problems. So we'll start out with Brandon Schlinker's talk. Brandon is with Facebook and University of Southern California, and his award paper is called Engineering Egress with Edge Fabric, Steering Oceans of Content to the World. And take it away, Brandon.
Thank you for the introduction. Good afternoon, everyone. My name is Brandon Schlinker from the University of Southern California. Today I'm going to be talking about Edge Fabric, a system we built at Facebook to deliver traffic to end users around the world. So let's start off here with a brief overview of Facebook's network. Facebook has dozens of points of presence around the world and interconnects with thousands of networks. Now, that rich interconnection with those thousands of networks offers Facebook 2 distinct advantages. First, it provides us with short, direct paths to end users, which means that we can bypass transit providers that have traditionally been part of the internet hierarchy. Second, it provides us with substantial path diversity, meaning that for any given end user, we often have multiple distinct paths that we can use to send them traffic. Now let's dive a little bit deeper into what goes on in internet connection at a pop, and then I'm going to go into the challenges that exist for interconnection. So first, at every POP around the world, we have one or more edge routers. We establish physical interconnections or circuits between those edge routers and other networks. So in this case, we've established an interconnection with an end user ISP and also with a tier 1 transit provider. Next, we use BGP, or the Border Gateway Protocol, to exchange reachability information with those networks. So in this example, the end user ISP, we receive routes to their end users across the network interconnection that we've established with them. And we also receive a route from that tier 1 transit provider. Third, BGP at our router just selects which of those routes we're going to use. And in this case, it selected that route from that end user ISP directly. So what are the challenges to using all this rich interconnectivity? Well, our key objective here is to deliver traffic with the best performance possible. But the challenge to doing that is that BGP doesn't consider demand, capacity, or performance in its decision process. So let's take a look at what problems that creates. We have here a simple example. Facebook on the left is trying to deliver 5 gigabits per second of traffic to the end users in the ISP on the right. Now our router is configured to use those short direct paths that we prefer. And so as a result, it puts all of that load onto that upper path and everything's fine. Until later on in the day. Now demand has risen. We're now at 12 gigabits per second of demand. And again, BGP at that router can't adopt to demand or capacity in real time. It's simply not possible to express that with BGP's policy terms. So as a result, the router continues to make the same decision, and it ends up overloading that link, leading to packet loss and degrading user performance. Likewise, BGP doesn't consider performance in its decision process. A simple example of that can be seen here. That upper preferred route now has a circuitous route on it, so it's added 50 milliseconds of latency. Also, some piece of equipment downstream is misfunctioning or malfunctioning, adding loss. So in this scenario, the route through that second route through that transit provider would actually be preferred. It offers us better performance, but we can't configure BGP to adopt performance in real time, and so we end up still placing all that traffic onto the less preferred, poor performing route. Now, despite all these problems with BGP and how it doesn't account for capacity or performance, it's still fundamental to interconnection, and it's not going away anytime soon. The thousands of networks that Facebook and other large content providers connect with all expect for us to use the BGP protocol. So what that means we need to do is we have to sidestep BGP's limitations. And what I'm going to talk about next is how we do that by shifting control from BGP at our edge routers to a software controller. So I've briefly gone over Facebook's network and an overview of the challenges. Next, I'm going to dive deeper into our connectivity and the challenges. Then I'm going to talk about how we sidestep BGP's limitations with Edge Fabric. I'll then talk about Edge Fabric's behavior in production. And finally, I'll talk about the evolution of Edge Fabric and some ongoing work. So back to those points of presence that we have around the world. At each of those, we have 3 types of connectivity. First, we have transit providers, and transit providers can deliver traffic to the entire internet. At each POP, we typically have 2 or more of these for redundancy, and we connect with them through a private circuit, or sometimes known as a private network interconnection. Then we have peers, and we separate peers into 2 different categories. I'm going to go into detail on why we do that a little later. But in general, we have private peers, on which there are on the order of tens per POP, and again, we connect with them through private circuits. And we have IXP, or public peers, that we interconnect with via internet exchange points. And those are on the orders of hundreds per POP, and we interconnect with them through a shared fabric, which means we don't have a direct circuit between our routers and theirs. So how do we prefer across these different routes? What's our routers configured to do? In general, we apply this very simple policy. We prefer routes from private peers over internet exchange point peers over transit providers. Now, we prefer peers over transits because peers provide us short, direct paths to end users. And we prefer private over internet exchange point peers because we prefer circuits that are dedicated to have dedicated capacity between Facebook and the peer. So as a result of that routing policy, the vast majority of our traffic actually egresses through these private peers. But that creates a problem because we cannot acquire sufficient capacity with our private peers to satisfy all demand. We always try to do this, but due to logistical constraints and business constraints, it's simply not always possible for us to establish sufficient capacity. And as a result, you can end up with scenarios like the one I illustrated earlier, where during a peak time period or perhaps during a failure, you have a link that becomes overloaded due to BGP's decision process. So how big of a problem is this? Well, to understand that, we did a 2-day study of 20 points of presence, which is a subset of a production network, and we identified circuits that would have been overloaded with BGP's default routing decision process based on the policy I described earlier. And overloaded here means that demand would have been greater than the circuit's capacity. What we found is that at 17 out of 20 points of presence, they had at least one circuit that would have been overloaded, and 18% of all circuits across these 20 POPs would have been overloaded at least once. Now, to further dive into how big of a problem this is, let's take a look at what the circuit peak demand is to its capacity for circuits where we predicted that the demand was going to be greater than its capacity at least once. And what I have here is on the y-axis a CDF of circuits where the demand exceeded the capacity. And on the x-axis is their peak demand relative to their capacity. So a peak demand here of 2 indicates they had twice as much demand as the circuit's actual capacity. So 2 key points I want to pull from this. First, 50% of circuits had peak demand that was greater than 1.19x their capacity. And then 10% of circuits had peak demand that was greater than twice their capacity, indicating that some circuits, 10% in this case, are drastically under-provisioned relative to their peak demand. So going back, again, BGP doesn't consider demand or capacity. And as a result, in these situations where demand exceeds capacity, we're going to end up with packet loss and degraded user experience. BGP's decision process in general doesn't meet our needs. We don't want degraded user experience. And that's why we built Edge Fabric. So next I'm going to talk about how we sidestep BGP's limitations by using Edge Fabric. And stepping back, that again involves shifting control from BGP at routers at the edge of our network to a software controller. So before I dive into what our implementation actually is, I want to talk about our 2 key design priorities here. First, we focused on maintaining operational simplicity, which means minimizing change and minimizing system complexity. Second, we wanted to have ease of deployment, which means we wanted to interoperate with our existing infrastructure and tooling. We have BGP routers at the edge of our networks, like most network operators do. We already have existing tooling for interacting with BGP. So we wanted a system which could interact with that existing infrastructure. So in general, there's 2 key extremes in terms of how you can do routing on a network. On the left-hand side here, there's what most network operators do today, which is traditional routing. I have my routers at the edge of my network perform or configure routes on a per destination basis based on what they've learned from BGP. On the right-hand side, I have another extreme, which is host-based routing. And that's where each host makes a decision on what the route of that packet's going to be, and then uses some signaling method, such as MPLS or GRE, to signal to the routers at the edge of the network how to handle that packet. So Edge Fabric's approach is balanced between these 2 extremes. We have a controller that overrides BGP's decisions at the router, and our hosts provide hints on packet priority, but don't precisely specify how the packet should be egressed from our network. So what does this approach look like? Well, first, routers at the edge of our network keep selecting routes like they do today using BGP. We still have all of our BGP sessions with other networks terminated at those routers. So in this case, our router, based on all the information that's received, has selected route A. Edge Fabric also selects ideal routes, but in addition to all that BGP routing information, it also has access to other inputs. In this case, that means advanced policy information, such as, for instance, us configuring based on business reasons or reasons provided to us by a peer, prefix traffic rates, circuit capacities, and route performance measurements. So Edge Fabric takes all of that additional input, and it also makes a decision. And in this case, it's decided to use route B. So our router and Edge Fabric have chosen different routes. We need to resolve this. The way we handle that is, in this case, Edge Fabric injects an override to that router using BGP, which I'll go into a little bit later, and forces that router to select the route that Edge Fabric prefers. So Edge Fabric can perform two types of overrides. It can override BGP's decision in order to move traffic for a set of end users. So for instance, we can say on a per destination basis, override what BGP would typically do, which is perhaps send that traffic via a peering link and instead send it via a transit link. It can also move a specific class of end user traffic. So for instance, I can send low priority traffic, which is perhaps non-video traffic, over which would have traditionally or by BGP been routed over my peering link, and I can instead shift that to a transit link. So let's take a look at how all of this comes together to prevent congestion in our network. And we're going back to that example I showed earlier, where we have Facebook on the left trying to deliver 12 gigabits per second of traffic to this ISP on the right. And BGP, by default, is going to put all of that traffic onto that upper link because we always prefer those short direct paths from peers. And as a result, that link's going to become overloaded. So what Edge Fabric does is it understands that this 12 gigabits per second of demand is actually composed of two prefixes. And in this case, it understands that if it shifts one of these prefixes away and shifts that traffic to an alternate link, in this case, the path via the transit provider, that it's going to prevent congestion on the peering link without causing congestion anywhere else. So how does this work at the BGP level? Well, we take that transit route that we've selected, we inject it via BGP, and then BGP at all of our routers is configured to prefer routes from Edge Fabric. And we do that by configuring local pref on the BGP sessions for Edge Fabric such that the local pref of its routes is always the highest and thus preferred. So Edge Fabric monitors BGP's decisions and overrides them as needed to prevent congestion in our network. Edge Fabric is able to support a variety of traffic engineering policies because it operates over a variety of inputs and it can perform overrides on a variety of granularities. And more importantly, it's compatible with our existing BGP infrastructure, which means that what we've truly achieved with Edge Fabric is centralized control over the traditionally distributed BGP decision process. Going back to those design priorities I introduced earlier, Edge Fabric meets our goals of operational simplicity because we can always fall back to BGP at the routers if Edge Fabric fails. It allows operators to continue to use our existing tools because routes are injected to those routers via BGP. And synchronization is only required between Edge Fabric and routers. Likewise, it meets our goal of ease of deployment. BGP sessions with external peers remain at those routers. We don't need to shift them elsewhere in our network. And we use industry standards for route and traffic information such as BMP, IPFix, and SFlow. So let's take a look at how Edge Fabric behaves in production and in particular criteria that we use to evaluate its performance. Edge Fabric entered production in 2013 with the primary objective of preventing circuit congestion that we were seeing on peering circuits at that time. It runs per pop and it executes every 30 seconds, meaning it takes in both route information and current traffic information and then determines based on its decision process where traffic should go and then injects routes via BGP. It controls 100% of Facebook's global egress traffic. So one of the things we have to decide when a link is projected to be overloaded, which means that Edge Fabric believes that the demand would be greater than its capacity, is how much traffic Edge Fabric should move off of that link. Now, if we move very little traffic, only enough to get down to 100% utilization, then we're going to end up with packet loss during bursts. Likewise, if I move a significant amount of traffic and now I'm at 50% utilization, now I'm getting poor utilization of those short direct links. And I'm not making good use of my capacity. So in general, what we strive for based on operational experience is achieving 95% utilization. And this allows us to have high utilization with tolerance for bursts in traffic. Now, the key question here is, can we maintain that utilization without any packet loss? So what we're going to look at now is two key questions. Can Edge Fabric prevent circuit congestion and packet loss? And can we keep the utilization of circuits at that 95% threshold? What we did here is we measured across our network during that 2-day measurement period. And what we found is when Edge Fabric is shifting traffic away, meaning that it believes that a link would be overloaded if it didn't intervene, 99.99% of the time, there was no packet drops on that link. Likewise, when Edge Fabric wasn't active, which means it wasn't shifting traffic away from a link, there was no packet drops. So this means that Edge Fabric intervened when needed, and it successfully prevented circuit congestion. Now, the next question here is, can we keep utilization at that 95% threshold? And to analyze that, what we did is we looked at the circuit utilization against the threshold every 30 seconds for circuits where Edge Fabric was actively intervening. And in this figure, what we want is as much around that 0 mark as possible, because that means we're keeping the utilization right at that 95% threshold. Anything to the left means that the utilization is lower. Anything to the right means that it's higher, and we end up with potential loss during bursts. So what we find here is that the vast majority of the time, we're able to keep the utilization of these interfaces or these circuits within 2% of that threshold. So Edge Fabric is able to successfully prevent circuit congestion and packet loss, and it can do that while keeping circuit utilization at this high threshold. So now I'm going to talk about the evolution of Edge Fabric and some ongoing work. So I talked earlier about those two extremes of how you can have routing decisions made at the edge of your network at routers, or you can have routing decisions made at your hosts. And when we actually started off with Edge Fabric, we were doing the other extreme, routing decisions made at our hosts. That's called host-based routing. So in this model, what Edge Fabric would do is it would inject its decisions directly into our servers. And then our servers would use MPLS, DSCP, or GRE, depending on the generation of Edge Fabric this was, to signal to routers at the edge of our network, send this packet through circuit X. Now, a key challenge there is maintaining synchronization. You have to keep routing state maintained across all of your hosts. And if, let's say, circuit X disappears, my servers need to know that now that it's no longer a valid option for them to route traffic via. In comparison, what we do today, this edge-based routing approach that I described, has Edge Fabric inject its decisions into routers at the edge of our network, and overrides are enacted by those routers. Hosts don't signal the precise path that they want a packet to take. Instead, they just signal to the router information about that packet's traffic class, such as this is a video packet. So this means that we don't have any host synchronization, which in our network drastically reduces the complexity of a system like Edge Fabric. Further, we have flexibility with DSCP signaling because we can account for different classes of traffic, and we can always fall back to BGP at our edge routers. So both of these approaches provide the capabilities we want today, but in general, Edge Fabric is best aligned with the design priorities that I described earlier. The next thing I want to briefly go over is about congestion beyond the edge of our networks. And for this example, I'm going to talk about internet exchange points. So internet exchange points allow networks to interconnect through a shared switch. So in this case, Facebook and another content provider may both connect to this big IXP shared switch, and downstream end user networks may connect as well. So internet exchange points are often seen as removing barriers to interconnection. I don't have to provision cross connects between me and all of these other networks that I want to interconnect with. But they also create a key challenge, and to see why, let's take a look at this example. In this case, both Facebook and this other content provider have hundreds of gigabits per second of capacity to this internet exchange point switch. In this case, Facebook wants to send 8 gigabits per second of traffic to those end users, and the other content provider 6 gigabits per second. Now, the problem here is that ISPX, they only have 10 gigabits per second of capacity. And as a result, we end up with the same problem that I illustrated earlier. Demand here is greater than available capacity. We're ending up with congestion and packet loss. Now, the key problem here is that these networks on the left, Facebook and this other content provider, have no visibility past their network edge. They have no understanding of what that other network's circuit capacity is downstream. And even if they did, they can't see each other's traffic. From Facebook's perspective, 8 gigabits per second is fine for a 10 gigabit per second link, and likewise for the other content provider. Now, this isn't just a problem for internet exchange points. It's anywhere past your network edge, you simply lack visibility. I can't see into what a private peer or an internet exchange point or a transit provider has as problems downstream. So what can we do to identify congestion beyond the edge of our network? Well, we've looked at a few different signals before. We were looking, for instance, at prefix traffic rates, so I could figure out how much of Facebook's traffic is going to go on the circuit. Again, that doesn't work here because cross-traffic beyond our edge from other content providers is being mixed in, and we don't know how much traffic they have. Circuit capacities, oftentimes you aren't going to know downstream. How much capacity does my transit have with the end user network? I have no idea. And what that means is you have to instead use route performance measurements. You have to infer congestion from these performance measurements, but that can be particularly challenging because you can see things such as latency increases, and you aren't sure as to whether that's due to a path change or a change in client population or due to actual congestion. Likewise, you don't know how much traffic to shift. You have to continuously probe for capacity. As downstream, a failure may occur, reduce capacity for 20 minutes, and then be resolved. So it requires a trial and error discovery process. Likewise, those interactions with other networks also create complexity. They may also respond to congestion signals and thereby reduce the amount of traffic they're putting on those links. And you may increase your traffic and you may oscillate together. So it's very difficult to get a signal here as to how much traffic should I put on this link. Even if you know the current status of congested or not, that doesn't mean that 5 minutes from now it's going to be in that same status. So stepping back from all of this, what's really new here? These problems in general have been known for quite some time. BGP hasn't considered demand, capacity, or performance ever in terms of the interdomain setup. And what we see as new here is the scale of connectivity, traffic, and quality of service demands that both content providers and end users have. And that brings new challenges and opportunities. So stepping back again, those rich interconnection that I described earlier, it offers content providers like Facebook a number of advantages, providing short, direct paths that can bypass transit providers and substantial path diversity. But in terms of meeting our goal of delivering traffic with the best performance possible, we're challenged by BGP's limitations because BGP doesn't consider demand, capacity, or performance. And as a result, we built Edge Fabric, which has allowed us to sidestep BGP's limitations by shifting control from routers at the edge of our network to software. And the result has been a more efficient network and better performance for our end users. And with that, I'd be happy to take any questions. Thank you.
There's a question that came in from a remote participant. Bruno asked, how does the controller tell a router to redirect traffic for a specific class of traffic? For example, do you use BGP flow spec?
So in this case, what we have actually at each router, there's multiple routing instances. And those routing instances, the DSCP marked packets arrive at each instance based on the DSCP value. So for instance, DSCP value 50 will arrive at routing instance 50, and we inject routes into each of those instances. If there's no route injected, the router will fall back to the default routing instance. So this allows us to customize on a per destination, per classic traffic class as to whether or not we're going to override the route.
He says, thank you, crystal clear. Okay. Don't forget to say your names.
Kathy Aronson. I'm just curious, do you have any mechanism for ingress traffic, or is it just that your traffic is so heavily egress that this is the most important?
Yeah, I would say in general, our traffic is primarily egress, so it ends up being a much larger problem for egress traffic. For ingress traffic, it comes down to more of load balancing using DNS entries or other things like that to send between POPs.
Aaron Falk. So it seems like one of the effects of this mechanism is that it increases sort of the dynamics of route changes that packets experience. And I'm wondering if you've looked at the impact that this has on individual flows. I mean, my experience with Facebook is that most objects are pretty small, but it's unlikely that both paths are going to have the same latency, and so for a particular flow, if you get switched, you're going to have things like reordering. And are there? Have you looked at sort of how much traffic is shifting when you make these decisions? How many flows are interrupted? That kind of thing. Like, how much of an impact is this?
Sure. So the way the decision process works today is it's likely going to continue to select the same routes or the same destinations to shift as the load increases. So let's say I'm 100 megabits per second over my capacity. I'll choose X to shift. Now I'm 200 megabits per second. I choose X and Y. And what that means is that once we've shifted something over, we're likely to continue to shift it. It's not always that we will. There is some level of optimization there where we can change what we're shifting over time. But as a result, we don't end up with rapid oscillations for the same set of flows.
And do you have any statistics on how much shifting is happening?
I don't have any statistics in terms of how much shifting is happening, no.
Okay. Thanks.
In general, I expect that for TCP, in terms of the reordering problem, it would be very brief on the flows that we're actively transmitting at the time. And yeah, we can take this offline further, Ed.
Hi, Brendan. I'm Dave Plonka. Neat idea about injecting the BGP prefixes, and I guess the failure mode then is if the edge fabric doesn't work, it falls back to BGP. I was wondering about, you gave an example where you showed two non-adjacent v4 prefixes aggregating to more than the bandwidth on the 10 gig, and you selectively chose one to offload, say, 2.5 gigs of traffic or something.
Right.
Where did you get those prefixes from? Do you synthesize them from what you know is downstream, or are they pre-configured? What degrees of freedom do you have to make more specifics or things when you have a peer that has a bunch of aggregate prefixes? Sure.
So the general aggregation here is we get samples from IPFix or SFlow. We aggregate them up to the most specific prefix advertised by a BGP. And then we do break those prefixes apart again further. So let's say I have a /20, which is 1 gigabit per second of traffic. We'll break that /20 up into smaller prefixes, /21 or /22, until we get down to a certain granularity. So in this case, I think we discussed in the paper splitting up until we get at least 250 megabit per second granularity, which would mean that then when we're shifting traffic, we can shift in 250 megabit per second buckets. So that allows us to keep that utilization at that high threshold.
Okay, and then one other thing about the prefixes that was curious to me is you showed a V4 example, but you guys are heavily V6 and do both. Do you make any effort to find the corresponding V4 and V6 prefixes and move them together, or do you treat them independently?
No, the decision processes are independent. We actually prefer to move V4 before V6, and that's because V6, we've seen cases where you shift it to a different route. That route is actually black holing the traffic, and then you end up oscillating because you shift away and back each time, the prefix. And this is likely just because of V6 routes being less groomed than V4.
My name's Stuart Cheshire from Apple. Throughout the presentation, you talked about demand as being a fixed thing. Like we have 12 megabits of demand or 12 gigabits of demand going into a 10 gigabit pipe.
Right.
But if all the transport protocols I know, like TCP and QUIC, adapt the throughput. And if you send a sustained 12 gigabits into a 10 gig pipe and lose 20%, it's not going to continue losing 20%. The senders are going to slow down that rate. So I didn't understand why the normal congestion control algorithms to adjust rate did not slow down when they're too fast, and conversely speed up when they're too slow. If there's excess capacity, TCP will speed up until it uses all the capacity, because there's no such thing when I'm looking at Facebook as loading a picture too fast. right? I want it to load as fast as it can, which should be all the capacity that's available.
So to be clear here, when I say 12 gigabits per second of demand, that's what our controller sees as the demand to that prefix at that moment in time. The reason that it can be greater than that link's capacity is likely because we shifted traffic away from that link on a previous iteration. So I may have, let's say I have a single prefix that if I was to send all through this link, it would be congested. I would have shifted it away on a previous iteration. Now its utilization has been able to continue to climb. And so now we're actually above what the link's capacity is. In terms of the transport protocols reacting, you're right, but you're still going to end up with a poor user experience, as you're still going to end up with packet loss in order for those transport protocols to react. Also, many of our shorts, our flows are very short, which means that you have a lot of flows constantly going through slow start, which means that they're going to end up interacting poorly when you're ending up with a lot of congestion in the link.
Thank you.
Vasily Dalmatov, Kryptonite. It's not a question, it's quite a remark. You are struggling with the good old problem of a congestion link, the information about congestion. So you stopped just one step before reinventing frame relay and means of struggling with congestion in frame relay. I hope it will be a result of your ongoing work and you propose something like beacon for the BGP. Thank you.
Joe Abley, this might be in the paper, I haven't read it, but you implied, I think, when you were looking for congestion off-net through exchange points or in remote networks, that you're doing active probing to look for congestion conditions. And I was wondering if you'd considered pulling those kinds of insights directly from TCP, where you already kind of have, with a passive observation, some indication of whether transport protocols are being throttled even before packet loss exists.
So we have an extensive TCP pipeline that we look at these events on. That's other work that we're looking at publishing. So.
Rüdiger Volk, Deutsche Telekom. I wonder that the primary and first control that you have for directing your traffic seems not to be mentioned, and well, okay, feedback not explained. And the first thing that you, I guess, are doing is the server selection, deciding to which of your server clusters at which location you direct the queries of these of the customers. I guess some well, okay, essentially the predictions of how much traffic will be generated this way from each of the server clusters goes into Edgecast, into Edge Fabric, as the estimation of the required or of the generated demand for the volume. But kind of, I wonder, is there no feedback that actually feeds back? We are having a difficult situation for one of the connections of server clusters, and please reshape the distribution of traffic between the servers.
So to be clear, there's two controllers here. I don't talk about the other one. There is a global controller, which decides which point of presence around the world an end user's traffic will be sent to. And then there's this local controller, which at each point of presence decides how we're going to egress that traffic. Those two systems do have some cohesion between them. Okay. And the interactions that you described do exist. In terms of how we decide what the demand is for each point of presence, that's not based on the global load balancer. That is based on IPFix or S-flow measurements at that local POP. So that allows us to get in near real time, every 30 seconds, exactly right now, how much load there is at that location.
Thank you so much. Well, you can ask more questions by the Jabber if you like, but anyway, thank you, Brennan, for a great talk. And our next speaker is another ANRP 2019 awardee, Florian Streibel, who is at Max Planck Institute Saarbrück, And his topic is BGP communities, even more worms in the routing can.
Thanks for the introduction and thanks for having me here. And I think I should adjust that. Okay, so this talk is on even nearer. Well, so this talk is on a paper at IMC last year. As already mentioned, even more worms and routing can. And full disclosure, part of this work was presented at last IETF meeting by Randy at GROW, but now you will get the full take. So we were looking at BGP data that we collected, and if you follow this development, you see a large increase of BGP communities being used. Over the last 8 years, we have seen more than 296% of increase of BGP communities being used, so individual values in BGP communities. And I looked up yesterday, it further increased, so last year around 5,000 ASs were using BGP communities, and now it's up to 10,000, and we see 74,000 individual values for short communities. So for me as a researcher, this means I should probably take a look what's actually happening there. So what are we talking about? We are talking about the short BGP communities. You probably know they are defined in RFC 1997. They are a 32-bit value, usually split in half, so the first 16-bit being an AS number, the latter 16-bit being a value where each peer or each AS is agreeing upon values with their peers, what they should mean or what they are being used for. So there is no strict semantics in it. Peers have to agree upon it on themselves. And as you have noticed, it's only 16 bits, so we now have AS numbers which are larger than 16 bits. Finally, we get the large communities defined in RFC 1892, and they are now at 12-byte values. So now we have three fields, each with significant space to use them. So 4-byte ASs can actually use communities now. Here, the first 4 bytes are now defined to be a global administrator, so it's now clear that this is actually an AS number, and this is the network defining the meaning of the community. So this is actually a good thing. Besides the confusion of the naming, if it's long or large communities, we spotted other problems when we tried to do our measurements. Large communities were not really used in 2018. We only found 51 global administrators actually using them. So nothing we could actually measure on the internet scale. This has become better, and if you're interested in the uptake of large communities, Emil from RIPE has set up or has published an article where he looked into the development of large communities and the uptake. So now we have around 120 global administrators that are using large communities. So, but how are they being used? In general, communities can be split into 2 groups. We have informational communities that have passive semantics. They are used for location tagging, where has this prefix been learned, in which pop RTT tagging we have seen. And on the other side, we have action communities that carry active semantics. They are used for triggering backhauling or actions in other ASs, for example, path prepending. The problem here is, without documentation of these values, you cannot see if this is an active or passive community, or if the semantics is active or passive, because as already mentioned, the peers decide themselves what these community values mean. There is no bit indicating if it's active or passive or an action community. And this leads into several sorts of problems. So, given the increasing popularity of BGP communities that we have seen, and the ability to trigger actions in other ASs with communities and relay information between ASs, the first question for me as a network researcher or science guy is, what could actually go wrong in using them? And we found out several things can go wrong. And the first thing we noticed is, when we looked at how communities propagate, people seem not to expect them to propagate widely through the internet. Although we have 2 RFCs actually defining how communities should propagate or should not propagate. RFC 1997 states communities are a transitive optional attributes, so they should be forwarded to your peers. And RFC 7454 says you should scrub communities you are using inside your network, so you cannot be manipulated from outside, but forward foreign communities by other ASs. So it should be expected that they are actually propagating through the internet. Still, a lot of people do not expect this, and a lot of transit providers don't actually forward them. We only found 14% of transit providers propagating received communities. And yes, this value seems to be small, but the internet graph or the AS graph is highly connected, so you actually end up in communities traveling quite a lot. But still, many people do not expect them to propagate it widely. And the problem here is that this leads to some potential for misuse. As they are propagating through the internet and can trigger actions multiple hops away, and there is no way for an operator to find out if this is intended or not, this leads into a problem. You cannot say, well, this is traffic management and this is legitimate, or this is an attack. And we ask ourselves the question if there are also unintended consequences in this combination of BGP communities being transitive and forwarded and used for actually changing routing decisions. And our assessment in the end is, yes, there is a high risk for attacks, and we already see some attacks as well. So what we're looking at, of course, we took all of the publicly available BGP data we can find. And in the end, we find that 75% of BGP announcements that we looked at have at least one BGP community set. And in 2018, it were 5.6 thousand ASs. Now it's more than 10,000 ASs that make use of these short communities. Now, taking a step back and looking at the propagation again, what we can actually measure or what we cannot measure, we have this very complex topology of 4 ASs, where AS1 is announcing a prefix P, and this is recorded in AS4, which could be a collector or just a simple peer, with the AS path 4321 as expected. And now AS2 is taking the prefix P with the community. In our case, 2:303. So 2 is the AS actually defining the meaning of this community, and this will be transported finally to AS4. So AS4 is recording this community in its routing decision in its RIP. So AS2 has added this informational community. Now AS2 is also adding a community for signaling or triggering an action in AS3, it's upstream. And this is also forwarded to AS4. So both of these communities are now present or visible in AS4, but AS4 cannot know who actually has added these communities, and so can't we. But we needed this for our measurements, so we had to come up with a solution. For us, we can only thus infer which AS is adding a specific community by assuming that if the AS value or the AS number present in the community is actually the AS adding the community, we will get a lower bound of the travel distance or of the AS hop count. This will lead us for the community 2303 with the correct travel distance of 2 AS hops, and with the other community 3123 with the wrong assumed travel distance of 1, of also 2, but it actually of 1 because it's just 1 AS hop. Although correctly it would be 2, but for us this lower bound of the distance of 1 hop is sufficient for our work. So if we plot these values, which again is the lower bound of travel distances, we end up with this ECDF. On the x-axis you see the AS hop count, and we find that 10% of communities have an AS hop count of more than 6, so they traverse more than 6 different ASs. From where we assume them to have been added. And more than 50% of communities still traverse more than 4 ASs. And if you compare this with the mean length of AS path that we have observed, which is around 4.5 or 4.7, this actually means it travels almost through the whole internet. And the longest community propagation we have observed were 11 AS hops. So they do propagate through the internet. Now, looking at another very complex AS topology, AS1 again announcing a prefix to AS2 and adding a community 3123 to inform AS3 or execute path prepending there. You will notice that this community value is also propagated to AS4 again. And although it's only intended for signaling something towards AS3, AS4 is also receiving an announcement with this community. So we end up with two different AS paths, and in the first case, we, for our research, call this community to be on path because the AS value from the AS community is present on the AS path that we record in AS3. In AS4, we call this community to be off path because the AS number 3 is not present on the AS path. It could also be that the AS that is being signaled for is further hops away behind AS4, but in both cases, this would be called off path because the AS number is not present on the recorded AS path. And if we now take the right part of these community values, separate them by on path and off path and plot this, we end up with this distribution. On the left side, you see quite a number of community values in the off-path communities that are related to black holing, remote triggered black holing. And on the other side, on the right-hand side, you see very even numbers that look like provider, like operator assigned and easy to remember. And we think that this comes from the fact that that ASs that are not implementing black holing will just forward black holing communities compared to ASs that do black holing, which follow the black holing RFC and do not further propagate these communities. So they will not be visible off path. Now coming to the experiments that we did to show that there actually are some problems out there in the internet. All of the experiments were done first in a lab environment and then validated on the internet with, of course, operator consent. And I will show two different scenarios in this talk. There are more in the paper, and the configuration of our routers are available publicly. So first, going back again and giving an intro, how does remote triggered black holing is supposed to work? So we know what we are talking about. AS1 is announcing a prefix to its upstream AS2 and then receiving traffic. This is expected behavior. Sometimes you have the problem that you receive more traffic than you actually want to attract. We call this a denial of service attack. And one mitigation is AS1 signaling to AS2 that it wants to black hole a prefix. Usually this is done in-band in the same BGP peering session than the normal BGP announcements are being sent. But there are also cases where it's a special BGP session which has other problems, but not the ones mentioned here. So AS1 is announcing the prefix P tagged with a black holing community to signal AS2 that it should drop traffic. AS2 is, of course, still announcing the prefix P to all its peers, but without the black holing community. Now what happens is AS2 is now dropping traffic, not routing the traffic towards P at its border routers, and the link between AS1 and AS2 is relieved from denial of service traffic and is usable. So you sacrifice parts of your network or parts of the prefix IP addresses to still keep all of the other prefixes and the servers reachable. This is how it should work. What we noticed is that for this to be used in a secure fashion, you need to employ some safeguards. Of course, the provider that is providing black holing has to check if the customer is actually allowed to black hole these prefixes, so if these prefixes are owned by the customer or the customer has permissions to black hole them. And this leads to the fact that you need different policies for customers and peers, different access control lists, and leads to a lot of configuration overhead for a secure usage of remote triggered black holing. And of course, in receiving such communities, you have to add no advertise and no export to the announcement, so you don't propagate it further. And we also noticed some providers translating black holing to the black holing communities of other upstreams. So you were not even able to do selective black holing because they were translating it and announcing it to their peers as well, translating the actual values. Now, what should not be possible is depicted here. We have the same topology, but now AS2 is in the role of an attacker, and AS2 should just be a backup path to the prefix of AS1, but AS2 is able to actually add the black holing community, although it's not on the best path. So AS2 is announcing to AS3 that prefix P should be black holed, and we notice AS3 is actually doing that. although the best path is through AS1, and AS1 is the origin for P, is not actually requesting any black holing. And the other problem that we noticed is that this is even possible if AS2 is not involved in any connection to AS1 at all. So AS1 can just hijack the prefix P and announce the prefix P with the black holing community set. And we noticed that in some cases, we are able to circumvent ACLs and prefix filter lists because the black holing community is checked before any prefix filter lists are applied. So we were able to confirm this on the internet. It works multi-hop, and it's hard to spot because the community values are usually not monitored. Reasons for that we found is the black holing prefix is more specific, so you need exception rules in your configuration to accept /32, so essentially everything that's smaller than /24. And some providers check the black holing community before applying any prefix filters. And we even found some configuration guides on the internet which had this problem, and they were the example configuration provided. And the problem here, there is no validation for the origin of the community. Every AS on the path can add the black holing community for the upstream provider. Now, yesterday, Job Snijders gave a talk at the IEPG where he presented a mitigation for this. If you would check that the peer that is announcing the black holing, or the prefix with the black holing community is on the best path and only then accept the black holing, this is one possible mitigation for this attack. So if you are interested in that, you should check the recordings of that talk. So if you only accept the black holing, if the peer that is announcing the black holing for a prefix is your current best path to that prefix, these problems go away. The second attack we were able to do was a traffic redirection attack. Again, AS1 is announcing its prefix P, and you see the current best path from AS6 to AS1 is through AS3 on the lower side of the topology. Now AS2 is our attacker announcing prefix P with community to do path prepending in AS3, which leads to the longer path over AS4 and 5 to be the preferred path for AS6. Why this attack could be interesting? Well, one thing could be there is a network tap between AS4 and 5, and even if you would identify that AS2 is your attacker, and you would screen the network of AS2, you will not find any network tap there because they on purpose redirected the traffic to AS4 and 5, where the actual network tap is. Could be AS2 is being forced to cooperate here. And the other thing it could just be a denial of service attack because it's known that the link between AS4 and 5 is a very thin link with not as much bandwidth as would be needed. So by redirecting traffic there, you could actually fill that link there. And after I gave this presentation at the RIDE meeting, we were actually approached by Dyn, and they pointed us to an article where they found attacks that today are actually already using communities to foster propagation of hijacks. So the attackers found out that by setting specific community values, their hijack would actually be propagated more in the BGP network. So we already see attacks using communities. So what now? We identified several topics where discussion might be useful. We found problems with authenticity, transitivity, standards documentation, and monitoring of community usage. Starting with authenticity, I mentioned several times that every AS that is on the AS path is able to modify, add, or remove community values on announcements in BGP, and there is no attribution possible. It means even if you found out that there is an incident, you cannot find out who's actually responsible for that. We all know RPKI, but intentionally this is not able to secure communities because we do want ASs on the AS path to modify routing and to add path prepending, for example. On the other hand, we also see that operators rely on the correctness of community values because they are basing policy decisions on, for example, where a route has been learned. And large communities are there, but they only partially improve the situation, because all of these points still apply to large communities. They only fix the first part of being an NAS number. So the question is, how can we achieve authenticity, or at least attribution? So after an incident, you know who you have to talk to prevent further problems in the future. Another thing that could probably lead to big discussions here is, we know communities are very helpful in debugging because you know what is happening in the network and why certain networks are forwarding traffic in a certain way. And they are indeed a very easy, low overhead communications channel and widely in use. We still only see them being used 1 or 2 hops away. You usually do not signal blackholing 5 or 6 hops away, or you do not usually need to inform peers 6 or 7 hops away. So on the other hand, you have a high risk for abuse in communities being transitive. So the question is, do we have a high risk here, or do we have more benefit? Do we need a discussion between benefit and risk using full transit, or allowing community values or communities to be full transitive? Monitoring is another field full of misunderstandings. We know there is no global state in BGP. It's a highly distributed system. And even if we look at all of the route collectors that are available, we will only see the end result recorded at these collectors. We do not know what has happened on the path between peers. Even if you are able to look into looking glasses manually, it's very hard to spot differences. So inferring modifications between the origin or the AS setting communities and the collector is almost impossible. And even if you would be able to record all of these changes, you still have the problem that you do not know what these community values actually mean. And there is no universal way for attribution of changes or recording who actually changed anything. So monitoring community values to detect abuse is extremely difficult in this field. And we have the other great field of standardization. In these short communities, ASN:value is still just convention. We cannot really be sure that the first value is actually an AS number. And there is no defined semantics. I know there have been a lot of discussions in the past that all came to the point that, well, we cannot define semantics here, but this leads to these problems stated. And by communities being used both for signaling and for triggering and not being able to distinguish what is what, you cannot even filter communities in a sensible way. And until now, there are only a limited set of standardized communities, and you cannot be sure if, for example, some AS is not actually using some arbitrary value for triggering backhauling. So standardization here might be a thing that should be further pushed forward. Doing our research, we found another very large problem. This is with documentation, because all of the ASs can define their communities themselves. There is no need for documentation. There is no central point of documentation. We found that some of the ASs are documenting them in WHOIS and IRR databases. On their websites, some are only providing community documentation in customer portals, or not even at all. So if you see a community, you cannot find out in an easy way what they mean. And even if there is documentation, it's often in a natural language, and parsing this is impossible. We tried, we failed. If you have a very limited scope, for example, trying to find out the communities used for geolocation or for geotagging of prefixes, you can, of course, look for city names, airport codes, things like that. But parsing community documentation in a general purpose, for a general purpose application, is not really feasible. So documentation is very limited and fragmented. It's very hard to actually find out a dictionary or find a dictionary for community meanings. Again, things are happening on that. I learned that DTAG has internally developed a system, what they call for community structuring. They are only using string representations instead of community values internally, and these string representations are then translated to short and large community values for their router configuration. An example would be tag.origin.country.de, where DE is a parameter for the community definition tag origin country. So you see it's a hierarchical system where it says, well, this community is a tagging community. It has passive semantics. It is tagging an origin on the country level, and the country is Germany. And their system allows the definition of parameters to communities, and these parameters with the communities together are documented in one system. They have working code, and they are using this in production already. Right now, they have an internal internet draft-like document, and if you are interested in that, you probably should talk to Rüdiger, who's sitting there and laughing. So I think this is a great way for actually starting to document communities in a sensible way, because you don't have to operate with magical numbers, and you can actually distribute these documentations and talk about policies and filters with your peers, because you can talk with strings and no magical numbers. And even if you have other router configurations, you can still use these string representations, and you know what you're talking about. Then we came up with some recommendations for operators based on our work. Of course, as the RFC already states, you should filter all informational community values that you are using that carry your AS number. So if you are using communities to tag where a prefix has been learned, you should scrub these communities when you receive them from your peers, because they are defined by you internally and used by you internally. It might be useful to come up with agreements with your downstreams, so to define what they are allowed to do with your upstreams, if they are actually allowed to do path prepending with your upstream for their prefixes. Of course, publicly documenting the communities you are using is key to enable other ASs to filter action communities to you. So if I have a customer where I know he might be playing around with BGP, I might want to filter things so he cannot trigger things in my upstream. But you need agreements for that, if you are actually allowed to filter these or not, or define what they are allowed to do. And one request, if you are providing public looking glasses, which is a good idea, please also show the community values that you receive. Otherwise, it's very hard to debug things. So coming back to the general problem, BGP communities are currently the only feasible way to realize signaling between ASs. But the problem is that the secure usage requires good operational knowledge and diligence. We do not think that a very over-complex system is really suitable to secure the shortcomings of BGP communities. But we have to be aware that there is a problem. And while everybody in this room is probably able to handle this and do everything correct all the time, we cannot rely on that on a global scale. There are a bunch of people out there who do not know what they are doing, and there will never be a world in which everybody is doing everything correct. So the question is, do we still can rely on, or do we still want protocols that allow people to make mistakes that will break other people's network? Or do we need an evolution in protocols here that are less fragile and more usable, or other, or to prevent people shooting themselves and others into in the foot? So wrapping up, communities are widely in use. They are used to realize policies. They are needed, but they heavily rely on mutual trust between the peers, because there is no authenticity and security in place. There is no attribution. Attacks are very hard to detect. And one takeaway from our experiments, we did some prefix hijacking that was reported on Twitter, but nobody actually spotted our redirection attacks based on communities. So we cannot be sure if there are other people already doing attacks using communities. If you're interested in more details, the paper is available. Here's the link. And with a picture of my cat, I'm happy to take questions.
We have time for a few questions if people want. I would start with a question. To what extent have the people who did this research brought forward any standards, any working group proposals to make the changes?
Again?
have the group who wrote this paper brought forward any work to the routing IETF side of the world about changes?
I think we did not yet, because we are in a state where we, well, assessing the problem and, well, showing everybody there is a problem.
Yeah. Okay.
And I don't know how to fix it, but
I thought this might attract Randy to the mic.
One of the Randy Bush, IIJ and ARCIS. One of the co-authors strongly objected both in working group last call and IETF last call to the black hole well-known community.
Understood. Randy Bush, everybody. Okay. Anybody else have a question?
Well, not so much question, but one comment is, when you say there is no authenticity, that is not completely true. The thing is, one has to recognize here that, well, okay, the community system is offering a range of stuff where operators can be creative. And you have, in the global system, you have to control the creativity and the interaction of the various creators. But in the end, you have to see that, yes, you always have bilateral relations that are mapped into BGP neighborship relations. And yes, what is exchanged there should be seen as something that is essentially just bilateral. And yes, if you want to be a responsible actor in the whole system, you have to really control what you are doing with your neighbors. And if you really take that understanding, you can actually start to build stuff that says, well, okay, you and me are peering. I'm a responsible person. I make an agreement what we are doing on our relation. And for that, if you and me are doing a decent effort at controlling, at doing the right policy for implementing our agreement, we actually have a chance for using that as fairly trustworthy. And I might even go out and offer you an agreement in which I promise you that I'm doing stuff where I'm relating to you in a controlled manner, the communities that Randy is sending to me. This is something that does not work recursively over the whole topology. But with that very limited and closed understanding, one actually can do stuff. And yes, having better documentation, having more tools for doing it will help a lot to do this right. Because a lot of the spreading of dubious information that you have observed is related to the fact that many of the operators just at the time when they 10 years ago did their policy, they didn't have good tools and they did not really take care of the responsibility.
But that was what I meant with, you have to talk to your downstreams to make clear what you are allowed to filter, because if you don't have any agreement,
exactly,
and you just strip all of their communities,
yes,
this could lead into other problems, even legally.
And that has to go with a very strict understanding into the BCPs that we are using.
Before you start, Jeff, people should forward around the blue sheets, and this will be the last question for this talk.
Very useful work. Thank you for bringing it. I mean, this is well known, and we've been facing this for the last 15 years, probably since mostly started doing remote black holing. The mitigation today is mostly basic hygiene. You take care of what you accept, and you take care of what you send. There are some intended consequences, in very useful stuff, things like bandwidth communities that are very useful in data centers. They were made non-transitive just to avoid these issues, while most data centers use eBGP, we cannot propagate this community. So there's work definitely needed that would allow us to use very useful stuff. Thank you again.
Okay. Okay. Thank you. Thank you. Okay, and last but not least is our ANRP 2018 awardee from who would have been in Bangkok but for visa issues. Oh, and that's Arash Molavi Khaki, and he is at Thousand Eyes now, and the work was done at Northeastern University, and taking a long look at Quick. Oh, can you click on the slides for him? It should be in there. Is it not? Okay. Yes, this is the case where we talked about at lunch where you give the talk without the slides.
Hopefully not. This is where the research group chairs can't work the laptop.
Colin, you're better than me.
This is loading. I just want to
working group chairs.
Add one note. I'm going to go through some background material and history of Quick. Oh no.
What's going on here?
To bring up to speed those folks who might not be super familiar with Quick. Perfect. So if you are an expert on Quick and you know the background material, I apologize in advance. Please bear with me as I go through it. All right, so I'm going to be talking about taking a long look at Quick. This was a measurement work that appeared at IMC 2017. And I don't think I need to convince anyone in this room that internet connectivity is important, but just to set the stage and put things in perspective, in 2015, 3.2 billion people had access to internet. Obviously, that number has increased over the past 4 years, but in that same year, the number of people with running water was less than that. Now, these two numbers next to each other are, I find them depressing, but for reasons that are out of the scope of this talk. But it emphasizes the importance of internet connectivity. We use it in our personal life, in our professional life. Virtually every business depends on the internet, and their viability is tied to the performance of the network that they're operating on. So naturally, there's a lot of effort to try to improve these networks and make them more reliable and more performant. IETF is one of those efforts. And we do a lot of things. We come up with new protocols. We use traffic management techniques to make sure that our networks are utilized in a way that everyone's demands are met. And we even design our applications to adapt themselves to the underlying network, so we increase the user experience, improve the user experience. And well, Quick is one of those efforts. It's a transport protocol. It stands for Quick UDP Internet Connection. And it started in Google, and it was basically a transport protocol designed with today's needs in mind. Quick was designed for a bunch of main reasons. The first one was to facilitate rapid deployment. What does that mean? If you think about HTTP, you have HTTP, hopefully you have TLS underneath, and it's running on TCP, which is your transport protocol. And as you all know, TCP is part of it's implemented in the kernel. So it's in the kernel space. What does that mean? That means if whenever you have a big change, let's say for TCP, and you want to deploy it at scale, everyone needs to update their operating system. And we all know that could take a long time. Windows XPs that are still around as an evidence to that fact. So Quick solves that problem by implementing in the user space. So now what this means is that whenever you have a new version of Quick, all you need to do is, let's say if you're browsing the web and you're using a browser, all the users need to do is to update their browser, and then they have the new version of Quick. Obviously, this means that a lot of things, like a lot of guarantees that the TCP provides, like reliable delivery, now all of those also have to be implemented in the user space, which I get to in a little bit what that means in terms of performance. But overall, this helps with rapid deployment. Another main reason was for Quick, which Google never shied away about pointing out, was to avoid ossification by middle boxes. We all know there are many middle boxes in networks. These could be NATs or security firewalls, or could be web caches and many other applications. A lot of them do claim that they improve performance. Perhaps in some cases they do, but there's also a lot of evidence that they actually do more harm than good. One of the examples that I find very interesting, this was a joint work by Google and T-Mobile. It was a few years ago. It was presented at Velocity Conference, where they basically looked at YouTube's traffic over T-Mobile's network and how does it interact with their web proxies. And this is a summary of findings from their slides. They basically found that it's better that YouTube traffic does not go through the proxies because they're hurting their performance. And I don't want to point any fingers to T-Mobile or YouTube. This is not an issue isolated to them. Another example, this is taken from a Cloudflare blog post where they were basically saying we had TLS 1.3 enabled for a while, but no one was using it because the browsers were not supporting it, and they were not basically turning it on because middle boxes were breaking it. And to be fair, it wasn't just middle boxes. There were other issues that prevented TLS 1.3 from being deployed at scale, but middle boxes were not helping. TCP Fast Open is another example that a lot of folks believed it never got deployed at scale because of middle boxes, and the list goes on. So, and all of these things can happen because in TCP, all of your headers are in the clear. So middle boxes can see them and act upon them. They can modify them, drop them, add headers, or break your connections into two, all the things that you're familiar with. Whereas in Quick, pretty much everything is encrypted. So you take all that from middle boxes. They can't do any ossifications or meddling. And finally, Quick was proposed to improve performance. A side note here, I have performance for HTTP traffic. I should mention that Quick is eventually going to be a general purpose transport protocol, but it started with HTTP in mind, and that's its biggest use case right now, and it's very integrated with HTTP. So throughout this talk, whenever I say Quick, we are basically going to focus on HTTP over Quick. So whenever I say Quick, I mean HTTP over Quick. So Quick improves performance by a number of optimizations. The most famous one is zero RTT connection establishment. If you're familiar with TCP, you have that three-way handshake to establish a connection before you can send any data. If you have TLS on top of TCP, as you should, well, there's going to be more RTTs. And Quick tries to achieve zero RTT connection, connection. What that means is that you can start sending data from the very first packet. Obviously, that doesn't always work. You should have contacted the server before and have valid keys for zero RTT to work. If you don't, then it's going to be 1 or 2 RTTs. But after that, everything else is going to be zero RTT. Quick prevents head of line blocking. What is that? If you have a HTTP stream, if it's HTTP1, you have a stream, you have to open a TCP connection. If you have more than one stream, then you have to open more TCP connections. And we all know that's not, that all those connections have overhead. They're competing over bandwidth. So it's not a great use of resources. HTTP2 solves this by multiplexing HTTP streams into a single TCP connection. This is great. It gets rid of a lot of overhead. However, if any of these streams is blocked for whatever reason, then all of those streams are blocked. And the reason for this is because TCP is agnostic to the HTTP streams. As long as TCP is concerned, you have a stream of bytes that needs to go from one end to the other end. And Quick solves this by basically mapping HTTP streams into Quick streams. Now, having that logic of streams in Quick if one of the streams is blocked, the rest of them are not going to be blocked and can proceed normally. Quick has improved loss recovery. It mitigates the ambiguity problem that TCP has. It has better RTT and bandwidth estimation. A lot of this good loss recovery comes from the fact that you can easily change the congestion control as well. So for example, if you have BBR, a new congestion control, you can easily replace your old one with the new one. And that comes from the fact that the first point that I talked about, everything is in application layer, so you can easily update things and deploy them at scale. And there are a lot of other optimizations that I'm not going to go into all of it, but basically Quick try to learn from decades of transport protocol evolution and take the good things that worked and put it into a single protocol. A little bit of history. Quick started in early 2010s at Google, as I said. I think it was in 2013 that it was publicly announced and Google started using it. Soon after, there was a spec draft, and towards the end of 2016, the IETF working group started, and the working group has been very active. There are many implementation of Quick around now. Google's Quick is at version 47 now, and the working group is working fast, and hopefully soon we're going to have a standard version of Quick, and everyone's going to be using that. All right, so that's why Quick started and a little bit of history of it. And but as I said, one of the main reasons for Quick was improved performance. So Google has been reporting on Quick's performance. They've been using it heavily, and they've been putting out reports that it helps with page load time, with YouTube rebuffering, and all these great numbers, that it's perfect and it's very promising. However, the issue with these is that they're all aggregated statistics and not really reproducible by anyone else unless you're Google and you have access to that data, and they don't really report any controlled tests. Again, everything is aggregated statistics. At the time that we started our work, there were other evaluations of Quick in the research venues. However, most of them were limited in environments and networks, limited tests, and they used old untuned versions of Quick, which I will get into in a bit what that means. And the results that they provided were not necessarily statistically sound. Neither they provide root cause analysis for the performances that they observe. So we basically wanted to bridge those gaps, like fill in those gaps and provide a more comprehensive evaluation of Quick and how does it compare to TCP. So as I said, we're going to look at HTTP's performance, and we're going to compare Quick and TCP. We have a very simple setup. We have a client on one end, which could be a desktop client or a mobile client. We have a server on the other end, which supports both Quick and TCP. And we have the network in between. We can emulate different conditions and see how the two compare to each other. Our servers host a bunch of web pages and objects with different sizes, and pages with different object sizes and different number of objects. And we fetch them using Quick and TCP, and we compare the performance. And I must point out that even though I'm not going to go into the details, once we get all the results, we run a statistical test to make sure any difference that we see is not due to noise or network variations or things that are not really differences between the protocols. So whenever we report a difference between the two protocols, we are confident that this is the difference in performance or not noise or anything else. So the setup is pretty simple, but in 2016, when we were doing these tests, we had this big issue of having a server that supports Quick. It's not like TCP. There wasn't a Quick module for Apache servers. There weren't many options around. So basically, our two real options were either use Google servers, because Google at the time had Quick, basically host our stuff on Google servers and run our tests against Google, or use a server that comes within the Chromium code base. Well, the first option, Google servers, didn't really work for us for first obvious reason that we had no control over it. So if we want to change something in the server or get some logs from it, well, we couldn't because we didn't own those servers. And the second issue was that we actually started seeing some unexpected behavior when we were testing against Google. And so here I have one example to give you an idea of what I mean by that. We uploaded a 10 megabyte object to Google App Engine, and then we downloaded it using our client. And this bar plot is, the red part is showing the time to first byte, and the blue part of it is showing the time that it takes for the rest of the download. And as you can see, there's this huge wait time. Like it's half a second. So basically 1/3 of our download time is wait time. And we did some tests. We realized this wait time kind of exists in Google App Engine. We weren't sure why it's happening. Obviously, we didn't have any control to the server to investigate this more. And this was not good for us because if we're checking performance and comparing millisecond times, a half a second wait time is not okay. So we decided to use the server in the Chromium. However, so this is the bar on the left is doing the exact same experiment, but with the Chromium server, the server that's part of Chromium. Now you can see that huge wait time is gone. That's great. But now our download time is much bigger compared to Google, I'm sorry. And this is problematic because this is basically these two plots next to each other are telling me that the server in Chromium cannot provide the performance that Quick is able to provide because we clearly see that Google is doing better. So we had to try to basically infer what are the configuration that Google servers are using and basically fine-tune our Chromium server to make sure it matches the performance that Google gives. So we did that. Along the way, we found some bugs, and basically we fixed it. I'm not going to go into the details, but happy to talk about it offline. But after we did that, the plot on the right, the bar on the right is basically the same experiment using our Chromium server after adjusting it. And not only we don't have that big wait time, now our download time is similar to what Google provides. And this is obviously not the only test that we ran. We did a bunch of tests, and this is not great, but we used Google as our baseline and matched our performance to Google. And I spent time on this slide to explain it because there were a bunch of research work before us that they did a lot of great work with Quick, but none of them went through this step to optimize the server, and pretty much all of them reported poor performance for Quick, at least in some scenarios, which for a fact we know it's because they were using a server that was not performant. All right, so now that we have our setup complete, our testbed complete, we did some tests. So I'm going to start showing you results from a desktop client, and I'm going to show you some simple results where we're downloading different object sizes from 5 kilobyte to 10 megabyte. And we're downloading them at different bottleneck bandwidths. And we're comparing how Quick and TCP perform compared to each other. So in this case, the RTT is 36 milliseconds. The loss is insignificant. And those numbers, so 45, 44%, what that means is that when we're downloading that 5 kilobyte object using Quick and TCP, the download time for Quick is 45% better than TCP. Now, to avoid bombarding you with a lot of numbers, I'm going to replace that with a heat map. So just think of it as red means Quick is doing better, blue means TCP is doing better, and white means there's no statistically significant difference between the two protocols. So if I complete this plot, you can see pretty much in every bottleneck bandwidth and for every object size, Quick is doing better than TCP. We're able to download the object faster, so this is great. We threw in some loss into the picture, and we saw still Quick is doing pretty much better than TCP in all cases. We increased the RTT time. We worked with different RTTs. In this example, RTT is 112 milliseconds. Again, Quick was doing way better than TCP, so far everything was great, and we were very excited. And then we did this experiment where we added some packet reordering, and as soon as we added packet reordering, things started to change. And we actually saw cases, especially when that's covering the plot, but the right side of the plot are big objects. The last column is a 10 megabyte object. So when we have packet reordering, Quick is doing worse than TCP. So we want to see why this is happening. We looked at Quick's code, instrumented the code, look at TCP to see how it's coping with packet reordering. And basically what we found is that TCP has this mechanism. When you have packets reordered, it increases its NAC, and it can cope with that reordering, whereas Quick didn't have that mechanism in place. And when packets were reordered deeper than its NAC, it was basically thinking that those packets are lost. So it was going into loss recovery, and we all know what that means, and it was that performance was going down. So we wanted to see if Quick can actually benefit from the same mechanism that TCP has. Our guess was yes, but we wanted to test it. So I'm gonna, I think this is not working. Oh, sorry, I went ahead. All right, so the NAC threshold, the default NAC threshold for Quick was 3. So we want to see, and I'm looking at the example when we're downloading a 10 megabyte object. So it's a big object, it's a sizable transfer. And we want to see if Quick can benefit from the same mechanism as TCP. So we started playing with the NAC, and we actually saw that there's a big latency between my clicker and the slide. And we saw that as we increase the NAC, Quick's performance actually gets better. And when we let the NAC to increase up to 300, which is actually the number that TCP, the upper bound that TCP is allowed to increase its NAC, then Quick is able to recover. It's able to cope with the packet reordering, and actually starts performing better than TCP. All right, so next thing that we wanted to look at was zero RTT, because that's a big improvement. That's one of the improvements in Quick. So we wanted to see how much zero RTT helped with performance. And I'm going to go back to our base example where there's no loss, and we have a 36 millisecond RTT. As I talked about, Quick is doing much better than TCP. This is Quick versus TCP. So this time we ran a test, and instead of comparing Quick with TCP, what we're comparing is Quick with zero RTT and Quick without zero RTT. And red means Quick with zero RTT is doing better. And as you can see in the plot, most of the plot is red, which is great. But also, as you have noticed, this benefit of zero RTT is really, you can really sense it when the object size is small. And when your object is big, naturally, because your transfer is longer and your connection time is a very small fraction of your transaction, so it doesn't have a big effect. Which is still great, because if you think about web, most of the time you're actually requesting very small objects. So this zero RTT can help a lot in those scenarios. Sorry. So comparing these two plots together, as we said, zero RTT only helps for smaller objects, but we can see that Quick is doing better for bigger objects as well. So we want to see what is it that the Quick does that helps it to perform better. So I have an experiment here, which is a little bit extreme, but I like it because it helps visualizing things a little bit better. So what we have here is we have a case that the bandwidth is changing between 50 megabits per second to 150 megabits per second. So it's a little bit of an extreme of an example. But we're downloading a 200 megabyte object, so it's a very long transfer using TCP and Quick. We're doing it back to back. That's what this plot is showing. On the x-axis, I have time, and on the y-axis, I have throughput. And as you can see, Quick is able to achieve a much higher average throughput compared to TCP, which explains why it's able to get such a better performance, especially when there's loss. So basically, the takeaway is Quick is way more aggressively and better adapting itself to the changes, to the available bandwidth, which is great, but also made us think, if Quick is so aggressive in adapting itself to available bandwidth, how is it going to play with fairness to other traffic? Because as we know, we want different flows to be fair to each other, so no flow shuts down other flows. So we made TCP and Quick compete with each other over bottleneck bandwidth, and we actually found out that Quick is not fair to TCP. We found out that Quick is taking more than share bandwidth. We repeated that experiment when Quick is competing with multiple TCP flows, and we still got the same results. And to make sure this is not our environment, we made Quick and Quick compete with Quick. Things were fair. TCP competing with TCP, everything was fair. But when the two protocols were competing with each other, Quick was not being fair to TCP. We want to dig in a little bit deeper. So here I have the congestion window size for the two protocols. In this example, they're both using cubic. And as you can see, they start from the same congestion window size, but Quick increases in congestion window and takes an unfair share of the bandwidth and causes TCP to basically slow down. And to zoom in, you can actually see that Quick is way more aggressively increasing its congestion window. All right, so I have one last thing to talk about before I run out of time, and that is mobile devices. So everything I talked about so far, the client is a desktop device. And again, going to my base example of no loss and 36 millisecond RTT, we saw that Quick is doing better than TCP in most cases. However, we redid the same exact experiment, but this time the client is a mobile phone. And what we saw is that, well, while Quick is still doing at least as good as TCP, you don't see any blue cells in there, but the performance gains of Quick started to diminish. So Quick is doing better than TCP, but the gap is not as big as for a desktop client. So we want to see why this is happening. And what we did, we instrumented the Quick code to try to infer a state machine and see what's happening in Quick and what states the protocol is in at every time. So I'm going to show you this state machine for the case where we're downloading a 10 megabyte object at 50 megabits per second. And it looks something like this. It's a classical state machine. You have different states, the percentage of time that you spend in every state, the probability, the transition probabilities. This is a little bit difficult to read, so I'm going to replace it with a table. And as soon as I do that, hopefully things are going to become clear. As you can see, when we're using a desktop machine, Quick is in application limited state for only 7% of the time. And that's the state that the client is receiving data faster than it can consume it. But as soon as you go to a mobile device where resources are more scarce, now Quick is in application limited state for 60% of the time. And this is exactly the price that Quick is paying for being implemented in the user space. You're constantly context switching between user space and kernel space, so which is fine on a resourceful device, but when you're on a mobile device, things are not that great. So that's all I had to talk about. To sum it up, we looked at the protocol that was rapidly evolving, and honestly, sometimes it felt like measuring moving sand. We did tests in a variety of networks and environments. There are a bunch of other tests that I didn't have time to talk about, but I encourage you to read the paper if you're interested in. And we instrumented the code, extracted some state machine, and that helped us to provide some root cause analysis for the performances that we were seeing. And finally, I just want to point out that this work was done 2 years ago. So at the time, Quick was at version 36. As I said, now Google Quick is at version 47. However, nothing stops us from doing the exact same measurement on the new versions. We actually did that in the paper. We looked at Quick from version 25 to 36, so we had that evolution of Quick's performance, and we can do the same thing for newer versions and future versions. And with that, I'm happy to take questions.
Jake Holland, could you go back to slide 19, please?
Sorry, the clicker.
Yeah.
There we go.
I wanted to ask, so this is very interesting, and thank you for presenting it. I wanted to ask, did you measure the retransmit rate in this bottom scenario?
Measure the what? I'm sorry.
The retransmit rate?
I think we did, but honestly, at the top of my head, I don't remember. I have to go back and look at the paper.
Okay, and okay, thank you. So that would be in the paper if you.
I believe so, but if it's not, I'm more than happy to dig in and find it because we have all the data. Like we didn't remove anything.
Great, thank you. And one follow-up, I believe it was 2 slides forward, perhaps 3, the fairness question. 21 or 20.
And I have a lot of.
No, forward. So slide 21 or 22, I think it was.
So if you want to go ahead with your question,
it's about the fairness. So what I wanted to ask about was you noticed the difference in the fairness where and I assume you mean that Quick was consuming a higher proportion of the bandwidth. Did you compare that to sort of the expectation as observed here that Quick performs better than TCP normally? So TCP will, this must mean presumably that TCP will leave some of the bandwidth underutilized or less utilized? And is it the same proportion here, or how far different is it?
I'm sorry, I don't think I understood the question. So you're saying if the bottleneck bandwidth was underutilized?
Right.
Like,
so my maybe this is too complicated to ask at the mic. But what I was trying to get at is that we expect that Quick will perform better than TCP based on the prior observations, even when they're not competing, right? Which means that on the same kind of link, TCP is must be leaving some bandwidth unutilized in order for Quick to be able to beat it, right? So how much is the fairness difference sort of disproportionately? Is it different than the difference between, and by how much, than the difference between their performance when they're not competing?
If I understood your question correctly, you're asking that if TCP, when not comparing, was basically leaving some of the available bandwidth on the table, and if the difference was
right. So it's like,
is
this really a competition fairness question, or is it just a yes, it is indeed running faster?
No, it's definitely a fairness issue because I don't know if this answers your question, but we did this for very long. So we let them both get to that equilibrium. And we could see that when there's no competition, TCP is able to utilize the bandwidth almost fully. If
okay.
That makes sense.
Thank you. Yeah. So so they all went to that 10 megabyte sort of where it's
when the transactions is long enough. Yes.
Excellent. Thank you. And sorry, one last one. The TCP was, both of them are running cubic, you said?
Yes. Yes.
Great. Thank you.
That was one of my questions. So I have a clarification question and a larger question. Clarification question is, what's the queuing discipline you're running in your bottleneck?
What's the what?
What's the queuing discipline you're running in your bottleneck link?
Are
you running BBR? Were you running red? AQM, Droptail?
I'm not sure.
Okay.
I have to go
Is
back
it in the
to-
paper?
I believe so, yes.
Okay.
Yeah.
I'll follow up if it isn't. The larger question is sort of going back to your very initial remarks. I'm really kind of, first, great work, very interesting, nicely presented. Thank you. This is a good paper. Thank you for coming here and presenting it. I'm interested in the 200 million users who have internet and no electricity, right? And so I think that there's a lot of attention being paid to Quick as higher performance and better utilization of congested resources. But I rarely see performance numbers when you look at things like very heavily multiplexed long RTT T1 links that have dial-up at the end, and users who are desperately trying to load simple web pages. And I'd be really interested in seeing some comparison. I mean, we really want to make sure those users don't get screwed if the world migrates from TCP to Quick. It's not great now, but ideally you wouldn't want it to be worse. So I'm wondering if you spend any time looking at it. There's a little bit here. You can sort of take the worst cases of all the things you presented and add them up, and maybe that's what it is. But
so I guess closest to that we experimented, we looked at some 3G mobile networks. So we ran some tests there, and we actually found out that our results showed that Quick is actually doing better than TCP, and it's in the paper. The reason I didn't put it in here, because the things that I put in here, I wanted to be cases that I can isolate and then show where the difference is coming from.
Yeah.
But and in networks that and as I said, we found in 3G networks and poor networks that Quick is still doing better than TCP, but most of our experiments were in controlled environments that were higher bandwidth.
Right. So I would just add to that you might look at adding very long RTTs in there, and then looking at things like fairness and seeing how that compares. That I don't have any intuition about how that would turn out.
I believe in our test we went up to 300 milliseconds of RTT, and
that's not yet one satellite hop, but it's a good start.
Yeah.
Christian Grothoff, you always say TCP, but I'd like to know, are you using TCP segmentation offload? Are you using TCP fast open, or are you using TCP from the 70s?
So, true. So I believe the segmentation offload is on. It's in the paper. We basically wanted to take a Linux box and use the TCP as is and don't change anything. And we did this on purpose because obviously you can optimize any protocol to...
Yeah, but on a Linux box, I can turn TCP fast open on or off very easily. It's a kernel option. I don't know what you did. That's why I'm asking.
Well, all the default values that came with it. They're all in the paper.
Gabriel Montenegro, Microsoft. So thank you very much for this work. And I think I heard you say that there may be some ongoing work going on, some more research. So if that's the case, could I add a suggestion that G-Quick or Google Quick is all fine and good, but the whole focus of the IETF effort is iQuick, right? The IETF Quick. It would be great, and there's several implementations out there that you could use if you would use those for the next phase of the testing, because that's a pretty different protocol, really, by today. And the best part of it is if you find something egregious or something that might need to be tweaked, then there's still time to go back to the working group and actually have an effect on the protocol if that's one of your findings. And that would be potentially more relevant for the future than G-Quick, because supposedly everybody at some point will be on IETF Quick. So that's one suggestion. And the other one is more of a comment. You indicated that since Quick is implemented in user space, that's one implementation. Ours, for example, runs kernel or user, doesn't matter. So you could run it in kernel, you could run it in user space. It's not part of the protocol itself, right? So I understand that for the testing you needed to do, of course, it was easier to get the user space, but
that's not really part of the protocol definition. So you could run it in kernel, and then maybe some of the disadvantages that you identified would go away in the mobile case, as you mentioned.
Yeah, that's a great suggestion. Yeah, at the time we were basically working with Google's Quick, and that was pretty much the only option we had.
Yeah, I understand. Yeah. Oh, thanks.
Okay, let's have a hand for Arash. Excellent ANRP talks. So to pitch for the remainder of the year, there's 4 more great ANRP talks to come. If you want the links and you can't find them for some reason, I did put up an agenda slide set that is in the tracker, so you can find that, and also a humorous Prague-related picture. But in any event, thank you for being here, and thanks for the great questions for our folks. And end of IRTF Open.
Actually, I have another thing. Since we're changing from one leader to another, I'd like everybody to really thank Alison for the work she's done in the past few years. Thank you so very much.
Thank you. It's been a pleasure. So we finished a little ahead even, which is good. And no horrible glitches with the... Yeah, I'm glad you were quick with that one. Yeah. Things are better now with the PDF slides than they used to be. Yeah, I have to go get coffee. Yeah. Oh, Colin, do you want to go? Yeah, probably you have to, but I think it would be worth your while to take a look at the Quirk tutorial after the fact.
Yeah.
Because